So now we're going to deal with B6. The one thing I'm going to note with B6 is that there's a small typo. This -3 should be a -2. It's a -3. Calculating the eigenvalues is very complex. I wouldn't expect it of you guys, but with it being -2, it's not so bad. So the first thing that we're going to do is we're going to figure out what the matrix representation of this expression is using the standard basis. The reason why we do this is because it's much easier to calculate the eigenvalues of a matrix. So this gives us 1, 2, -1, -2, 1, -1, 2, -3, 1. Now that we have the matrix representation, we can calculate the determinant of the matrix representation T alpha minus lambda I, where alpha is the standard basis. Now, to compute the characteristic polynomial, I highly encourage you not to expand early. Like terms can cancel. So if we look at the determinant of our matrix, 1 minus lambda, -2, 2, 2, 1 minus lambda, -3, -1, -1, 1, minus lambda, this equals 1 minus lambda times 1 minus lambda squared -3 plus 2 times -2, 1 minus lambda. And this should be a -2 plus 2 -1 times 6 -2 times 1 minus lambda, which is equal to 1 minus lambda cubed -3, 1 minus lambda, plus 4, 1 minus lambda, -4. If I copy this down right, this should be a -3. This is a -3. So we get -18 plus 6, 1 minus lambda, which is 1 minus lambda cubed plus 7, 1 minus lambda, -22. Now, if we expand this, we get minus lambda cubed plus 3 lambda squared minus 3 lambda plus 1 plus 7 minus 7 lambda minus 22. And this simplifies to be minus lambda cubed plus 3 lambda minus 10 plus 3 lambda squared minus 10 lambda minus 14. This is what our characteristic polynomial of T alpha is. And here, this might seem difficult to calculate the roots of, but you'll notice that the absolute value of these first terms equals 14, which is what we're subtracting. So if we look at the characteristic polynomial of -1, this equals minus 1 cubed plus 3 minus 1 squared minus 10 minus 1 minus 14, which equals 14 minus 14, which equals 0. This tells us that lambda plus 1 is a root. So we can divide out by lambda plus 1. So I have lambda plus 1. I take my polynomial and I divide out by it. So I go minus lambda cubed plus 3 lambda squared minus 10 lambda minus 14. This is going to be minus lambda squared minus lambda cubed minus lambda squared gives us 4 lambda squared. So plus 4 lambda minus 10 lambda, 4 lambda squared plus 4 lambda, giving me minus 14 lambda minus 14 minus 14 times my expression. 14 lambda minus 14, subtract them and we get 0. So this tells me that my characteristic polynomial lambda is equal to lambda plus 1 times minus 4 lambda, or equals minus lambda plus 1, lambda squared minus 4 lambda plus 14. I like to pull the minus sign out at this point to give us a positive quadratic. And now to figure out the roots here, I'm just going to use the characteristic polynomial. Lambda equals 4 plus minus the square root of 16 minus 4 times 14 all over 2. Lambda equals 2 plus minus the square root of 16 minus 56 over, and what I'm going to do is I'm going to do a trick of bringing it inside the square root, because this 2 is positive. I can bring it inside and it becomes a 4 inside. So lambda equals 2 plus or minus the square root of minus 40 over 4. So lambda equals 2 plus or minus the square root of 10 I. So we've got our 3 roots. We got lambda equals minus 1, 2 plus root 10 I, and 2 minus root 10. First thing to note is because we have 3 distinct eigenvalues, it is diagonalizable. So our matrix is diagonalizable, and if I wanted to have a diagonal representation, we could simply put these on the diagonals, but we need to calculate our eigenvectors. So to calculate the eigenvectors, we're going to find the kernel of T alpha minus lambda I. We're going to find the kernel of these vectors of T minus lambda I. And to find these vectors, we set up our system of equations, setting it equal to 0 and solve it. And for lambda equaling minus 1, that's something that hopefully you'll be able to do. I'm going to do it for one of our eigenvalues. I'm going to do it for this eigenvalue here. For the other eigenvalue and for lambda equaling minus 1, it's a very similar process. So the first thing that we're going to do is we're going to set up our system of equations. So we're going to look at 1 minus 2 plus root 10 I, 1 minus 2 plus root 10 I, and 1 minus 2 plus root 10 I, equaling 0, 0, 0. And now filling in the rest, we've got 2 minus 3 minus 1, and minus 2, 2, and minus 3. minus 2, 2, minus 3. Right? And this equals 0, 0, 0. So from here, what I'm gonna do is I'm gonna make this first entry here a 1 by, I'm first gonna simplify this expression to give us that this is minus 1 plus. Minus 1 plus root 10i minus 1 plus root 10. From here, solving this is actually quite complicated. You would normalize and reduce, and it actually becomes quite ugly. This is not the type of question we would expect to see in the exam. On the exam, we'd like this to be rather nice and neat moving forward. So with it, the expectation that it's nice and neat moving forward, we're not actually gonna have you guys have something this ugly as your reduction, having to solve this and simplify it. But it could be ugly, and there's process you can go through. So if you want to solve it, you can go through and solve it, but it's not gonna be pretty. In an exam situation, you would expect something to be much nicer to solve for, but you would simply solve these kernels. I will put up another example and go through another example where it's much nicer to solve for the eigenvalues and eigenvectors. And on the exam, the matrix that is being done on the problem that's similar to this, you'd expect something that's a lot more nice to work through.